Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's challenging level puzzle, and it's called Segmented Yin Yang Snake by A. Peterson, and here are the rules. Normal Sudoku rules apply, which means place the digits 1 through 9 without repeats in every row, column, and box. We can get a box here. Draw a one-cell wide snake of orthogonally connected cells that does not branch or touch itself. Now the question is, can it touch itself orthogonally? Oh, it can't okay. Okay, so draw a one-celled wide snake of orthogonally connected cells that does not branch or touch itself. Okay, and a further rule will clarify that. But basically, the snake is essentially a long line, which can never loop and touch itself again. And it can't branch, so it has to be continuous. So as an example, I guess this could be essentially an example of a valid snake. Right? Because it never touches itself, it never branches, and it's essentially, yeah. The non-snake cells must, and it's orthogonally connected. So, yeah. So orthogonally connected just means that they share an edge. So these would be considered orthogonally connected. This would not be a valid part of a snake because it's not orthogonally connected, which means sharing an edge. It's diagonally connected, but also, the non-snake cells must form a single orthogonally connected area. So the non-snake cells must basically be one large area connected to itself orthogonally, which means that it has to basically share an edge with a cell that's connected to all the other cells that are non-snake cells, right? And this is the yin-yang part of it, or part of this is the yin-yang. And then the other part is no 2x2 region can be entirely snake or entirely non-snake. So that's why I created this example, because there's no region here which is entirely snake or entirely non-snake. That's a 2x2 region. And so if the snake were to essentially, well, I guess technically, well, okay, it couldn't go here. It can't touch itself because then essentially it can't touch itself orthogonally or actually diagonally, because if it did, so say this was not valid, say this was actually green, it couldn't touch itself orthogonally, or sorry, diagonally even, because that would block off the non-snake parts from being one orthogonal region, orthogonally connected region, right? And in addition, you can't have a 2x2 area which does not have, which is entirely snake or entirely non-snake. So therefore, this would be invalid because there's a 2x2, there's actually multiple 2x2 regions which are entirely non-snake. But you can't have a 2x2 region that's also entirely snake. Therefore, you can't technically go this way either, right? So that's all for the snake. Well, actually, maybe not all. Digits separated by a white dot are consecutive, and these are called white Kropke dots. Digits separated by a black dot are in a 2-to-1 ratio, and these are called black Kropke dots. So as an example, if this were a 6, this would have to be a 5 or 7, because digits or cells separated by white dots must have digits that are consecutive to it, to each other. And then if this were a 4, not a 5, a 4, this would have to be a 2 or an 8 to maintain the 1 to 2 ratio, which must occur between cells which have a black crop key dot between them. Digits separated by an x sum to 10. So, for example, if this were a 3, this would have to be 7 because these two cells must add up to 10. Cells separated by dots or x's will contain one snake cell and one non-snake cell. So out of every set pair of cells separated by a dot or by an X, one must be a snake cell and the other one must be a non-snake cell. And box borders divide the snake into segments, each of which have the same sum. So this is a segmented part of it, and this is called normally region sum line. So the snake acts as one large region sum line. So let's see, do we have... We don't have that. Okay, so let's go back to the example I had previously. Even though it's not correct, obviously, because it doesn't fulfill the every dot separates a snake versus a non-snake cell. But if this were, say, the actual snake, then we would know these two cells must add up to the same sum as these three cells, which must add up to the same sum as these three cells, which must add up to the same sum as these two, which must add up to the same sum as these three, which must add up to the same sum as these 5, which must add up to the same sum as these 3, these 2, these 2, or sorry, these 3, and these 2. And that's how the region sum line works, which is the snake, right? The snake is one large line, essentially. One long line. And those are all the rules. And these would be different segments, right? Because the box borders divide it into segments. So this is a separate segment than this is. Because even though they're in the same box, this is the box borders divides it into separate segments. Well, those are all the rules. If you'd like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay, so out of every... That's interesting. Cells separated by dots or X's will contain one snake cell and one non-snake cell. Well, let's say this was a snake cell, right? If this was a snake cell, this would have to be a non-snake cell, which would mean this is a snake cell. I don't know if this tells us very much, though. These are interesting, right? Okay, so these have to be opposite, right? So I guess we'll make this, I don't know, red and yellow here. Okay. And these are opposite too. So these two are the same. We're going to make those pink, I guess, and this orange. These will make dark and this one medium. Well, if pink is a snake, it has to go here. If it's not, orange has to go this way. One thing you know, okay, that's actually interesting. Well, this isn't complete yin-yang, though. I was gonna say that you can't have... No, actually, that's true. Right, okay, so this is similar to normal yin-yang puzzles. I was gonna say that I didn't know if you could have these two be the same color, but they have to be, right? Or sorry, they cannot be. In a normal yin-yang puzzle, it's usually you have two contiguous sets of orthogonally connected cells, and they're separate, obviously, but one is essentially connected to itself, all orthogonally connected, and the other one is connected orthogonally to itself. Well, what happens if this is the same set as this? The problem is this essentially has to eventually connect somehow to here, and that would necessarily block this from orthogonally connecting to this cell. So that's how you know that in yin-yang puzzles, you cannot have a pattern where these two are the same set and then these two are the same set also. This, if you have two in diagonally connected and you have one that's opposite, you know that the fourth cell in that 2 by 2 area has to be the same as the two that are diagonally the same here. So therefore we know this cannot be yellow, it has to be red. This cannot be orange, so it must be pink, which makes this an orange. This similarly can't be medium gray, so it has to be dark gray. And then we're not really sure about anything else. One of these two are, but we don't know which. Hmm. Okay. Oh, that's interesting. So if this is the snake, that would mean this is only one in size, right? And that's problematic because then every part of the snake would have to be 3 length at most. It's possible, though. We just don't know. But this is rather unlikely. Um, but we can't rule it out that this would still be the snake, right? Now, these are in a 1 to 2 ratio, but that's not that helpful. This is all consecutive. So it could start from 1 to 2 to 3 to 4. 2, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, 7, 5, 6, 7, 8, or 6, 7, 8, 9. And this could be 1, 2, 3, 1, 2, 3, 4. So 4, 3, 2, 1. Could be then So these are 2 through 8, but we don't know. These can be the full 1 through 9, right? Hmm. That's interesting, though. So if this is essentially the snake, can it ever connect to the... I guess it could go down 3 and then cross. That's possible to be pink. Hmm. Ooh, excuse me. Hmm. One thing is that the snake... Well, you don't know. You don't know what the limit of the snake is, right? Oh, one thing is that for yin yang puzzles, anything on the border, once it swaps colors, you can never change back, right? Because it's similar to this area, right? If we were to say that this was like, I don't know, say, well, this obviously changes here. So say this is yellow and this is red. Well, this can never be yellow because if this is yellow, how does this connect to the other red without cutting the yellow into 2 segments? It can't. And either way, if it's a snake, which is all orthogonally connected to each other, so it's one long line, and therefore can't be broken in 2, or if it's the non-snake region, which must form a single orthogonally connected area, not 2, therefore this can never work. Therefore, we know these are all red, and these must all be yellow to connect to here, right? Otherwise, it's not going to work. Therefore, we know this is a red because no 2 by 2 area is all snake or all non-snake. Same as this. This is all red too. This then has to be red also. I'm thinking the yellow is likely not the snake. Actually, it can't be the snake, right? If the yellow were the snake, it goes here and then goes here, and then it can't enter in anymore, right? Because it's blocked by this. So the red essentially has to be the snake. So then we're going to make the red then essentially the green. And the yellow is the blue. It's the non-snake. This then cannot be green because it has to be part of the snake. This is green. This has to turn here. So this is green. This cannot touch itself, so this is blue. It has to continue here. This is green. It could go here as part of the snake. Ah, but this snake is already 4 in length. Therefore, this cannot be the snake. So, because otherwise this would be 1. We already have a 4 in length one, so therefore this has to be non-snake, which means this has to be a snake. This has to exit out some way, and it exits out that way. This has to exit out that way, and then continue here. One of these is, and one of these isn't. It could go something like that. That's possible. This has to go down here to continue. This cannot be a snake, so therefore that's that. This can't be a non-snake, so then it connects this way. This has to extend down here, which means this has to go here, which means this has to be non-snake. So it has to continue this way. We don't know about this. So this is 3. This is 5. So... Oh, wait, hold up. This is not correct. Because we don't... Right. It could stop at any time. So this actually doesn't have to go that way. We know that this cannot be part of the snake because this doesn't have to go that way. Okay, so that's one thing about the snake that's not correct. Okay. We do know that that has to be non-snake because this goes here and then goes that way, right? But this doesn't actually have to continue that way. We know these are the same. This doesn't actually have to continue that way either. Right. We don't actually have a guarantee that the snake continues. Well, one of these two has to be. It just doesn't have to necessarily... It could stop here. Right? Um... Oh. This cannot... What happens if we assume this is part of the snake? If this is part of the snake, right? So say it's dark and say it's green instead of dark. This would have to be non-snake, but then we have 3 non-snakes here, which would force this to be a snake. And then this would be a non-snake, but this would have to somehow connect here, which would make this its own orthogonally connected region, which is not allowed. So this cannot be part of the snake, so we then have shown that this has to be part of the snake then, right? This could stop here. We don't know. It's unlikely to, but it could. The snake part makes it a little bit difficult. Well, we still... Never mind. It's still like typical yin-yang, so we shouldn't be making those assumptions anyways. We wouldn't be making it in typical yin-yang. I just assumed since it was a snake that it had to continue, but it doesn't have to. Um... So it's at least 3 for each snake segment. So that doesn't tell us that much. It does mean that the sum of the region sum has to be at least 6. But that was always pretty obvious. We're gonna make this red and yellow too. So this is red, this is yellow. That doesn't really tell us much. If this were blue, this would have to be green, and this would have to be green because of the 2x2 area. This would have to be green because of the yin-yang shading, and this would have to be green. So I guess this would essentially be the snake. So then these would all be blue, which would force that to be green. But that doesn't work then, right? The snake can never be essentially... Right. The snake can't be, like, wholly just, branching. Well, it can't branch, essentially. So then this 2x2 area, how does that work? If it goes this way, it can't connect this way, so it has to connect here, but then this branches. If it connects this way, similarly, it can't go this way, but then this branches here if it goes this way. So either way, that doesn't work. So this can never be non-snake. This has to be snake, which means this is not snake. I don't know anything else about this, though. So this is non-snake. Ah, say this pink was blue, non-snake. One of these then has to be snake, and one of them has to be non-snake. But if one of them is a snake, that means it's branching. Okay, actually, we do have more information. None of these can be snake. They have to be all non-snake. Which means that this has to be snake. Right? Because specifically, you can't branch. So this is all snake, therefore it can't. None of these can be snake then. Which means these have to be snake, and these are non-snake then. And this is all because it goes that way, right? One of these parts has to extend. This has to be snake, which means this has to be snake to continue, because otherwise it would be touching itself. Well, it goes up this way, so this is not snake, which means this has to be snake. Oh, that's interesting. Well, where can this go? I guess it could stop here. Actually, it could stop here. That could be fun. Right, because it could go something like this. That's possible. We don't know which ones these are. Either way, so... Oh, wait, this can't be... These are different ones, right? So if this were blue, that would be green. So this actually has to stop here. So this has to be blue. Because otherwise we'd have essentially the cross index, right? We'd have this being green and this being blue, but that's not possible in a yin-yang puzzle. So this is incorrect. Therefore, we know this is blue and this has to be green. Which means, and again, it can't touch itself, so therefore this is blue. This is where it ends in one area, so this must continue here. We know then it has to continue. This has to well, it doesn't have to continue. It could be something along the lines of this. That's possible too. So it doesn't have to go down. But this is a set of 5 digits, which equals, and this is a set of 2 digits. So this then is, so the most you can have in any box is 5. But essentially this is 2. Hmm. Therefore, this cannot be 2, 3, or 4. Or it can't be 2 or 3 here. Because we know this adds up to what? At most... 17, right? Because these 2 digits by itself is a segment. So therefore, we know that this is at most 8 and 9, which adds up to 17. So this is 17 at most. And what digits are required to have 17? Well, you could have 1, 2, 3, 4, or 7. 4 and 7. 1, 2, 3, 4, 7. Or 1, 2, 3, 5, 6 for 5 digits. So this is 1, 2, 3. This can't... 1, 2, 3, and then any from 4 through 7. This can't be 8. And these have to be 4 through 9. But this can never be 9, right? And how does this work, right? You cannot have 2 here, so this can never be... How does this work at all? This can never be 9. It could be 8, 7, 6, 5. No, it can't be 8, 7, 6, 5. Because if it were 8, 7, 6, 5, the problem is that this would be 7 and 5. And what 3 digits add up with 7 and 5 to at most 17? There's nothing, right? 17 minus 12 is 5. And 3 unique digits can never add up to 5 from Sudoku. So this can never be 8. This is 4 through 7. This can never be 8. So if this is 7... Well, this can't be 7, because then this would have to be 6 and 8 surrounding it. So therefore, that can't be 7. This is 4, 5, or 6. So what's consecutive with that could be 3, 4, 5, 6, 7. This could be... cannot be 1 or 2. It would be 3, 4, 5, 6, 7. So can this... Similarly, this can't be 7, because then this would be 7, 6, 5. And then again, you would have a 5, 7 with 3 other digits to add up to 19, which is not allowed. Or 17, which is not allowed. So this can't be 7, which means this can't be 6. So this can never be 15. Because if it were 15, that would have to require 1, 2, 3, 4, 5. And this can only be 4 or 5. This can't ever be 7, right? Because if this is 7, it would have to be 8, 7, 6, 5, right? When we show that that doesn't work. So this can't be 7. So it could be 3, 4, 5, 6. So that's possible. Let's look at the other possibilities. So this is 3, 4, 5, and 6. 4, 5, 6 can work because it could be 1, 2, 3, 4, 6. 7. So this is specifically 9 here. And it's 7 or 8 with 9. Okay. This then can't stop here because otherwise it just doesn't work. Therefore, it has to be 2 at least. And actually, this cannot be just 2. Because if this were just 2, it would have to be the same 2 as these digits because it's either 7, 9 or 8, 9 because this can no longer be 15. It's 16 or 17 here. So we know the 9 is here, and we know that this adds up to So if this is 9, this can be 6 through 9. Oh, wait, 9 can't be here. So this is 6, 7, or 8. This must extend somewhere else, but we don't know where. It probably is that way, though. So it could be 3, 4, 5, 6, 4, 5, 6, 7. Can it be 5, 4, 3, 2? No, because 2 has to be in this set of 5. It could be 6, 5, 4. No, can't be 6, 5, 4, 3 either. So this is specifically these, right? It could be, it's okay. This could be 3. Hold up. If this is 3, 4, 5, 6, the problem is you have 3 and 5 here, and then you would have to have 1, 2, and 7 as the minimum, which would not add up to, which would add up to 18, which is not allowed. So this cannot be 3, 4, 5, 6. It must be specifically 4, 5, 6, and 7, which means the minimum now, or basically the complete amount, would have to be 1, 2, and 3, which means this is 7 or 9. So this can't be 7, because this adds up to 16. This is 8 or 9, and this is 8 or 9, but this can't be 9. Therefore, this is 8, which makes that a 9. This can't be 8, so this must be 6, which must be consecutive with 7, which makes that a 9. This must be 8, so this has to be a 9, because this is consecutive, but it can't be a 7 here. These 3 add up to 16 also. So what does that mean? What can it be that adds up to 16 here? It has to be specifically 3, 5, and 8 without 6, 7, or 9. So this must be 3, 5, and 8. We have a 3, 5, 8 triplet in column 1, which eliminates 3, 5, and 8 from the rest of the column. This can't be 3. These 3 then have to be 1, 2, and 4. So the remaining digits here are 3, 8, and 9. We also know that for 2 consecutive digits, you can't have 1 and 2 because that would eliminate all possibilities here. 3, 4, 5, 8, and 9 are all accounted for, so this must be 6 or 7. And this must be 1 or 2. Remaining digits here are 1, 2, 4, and 5 here. This obviously has to have 3. We don't know which. This cannot be 8. It could be 1, 2, or 2, 4. Or it's 3, 6. We're not sure. Either way, this has to be consecutive with this. So this is 1, 2, 3, 4, 5, or 7. It cannot be 6 because there's no digit here that's consecutive with 6. This also must add up to 16. I guess this could be 3 with 1, 2, 4, 6, so that's possible. At least one of these two is must be a snake. And if it's that one, this would also have to be a snake. So this one is always a snake then, here. And it goes here. So therefore this cannot, well, could go down here. No, it can't go down, well, it could go down here and just connect that way. No, because if it tried doing that, the problem is this is one end. We know this is already one end of the snake. So then this would have to break. This would have to be another end, and this would be another end, which is not allowed. So it can't go down that way. This would be an end if it doesn't connect. But then this would also be an end if it doesn't connect. Therefore, it must connect. Okay. This could stop here. We don't know. Oh no, but we have 3 non-snake cells here, so this must be a snake. If this is not a snake, we would have an end here and an end here, which is not allowed because we have 3 ends of a snake, which would mean there would be branching. So therefore, this must connect this way. Um, hmm. Can this ever connect this way? If it connects this way, okay. Yeah, if it connects this way, that's no good. Right? Because it would be touching itself technically, and then also it would be branching to go this way. So this is not allowed. It cannot go this way to connect to here. Can it go this way? No, because then this would be considered branching, right? Well, no, it could actually go that way to go like that. That's possible. Hmm. Okay, never mind. It could go that way. So it goes that way or that way. And this could be the end, right? Of essentially. Right, so we don't know anything about that one. This has to continue. It can't be 2 because it would, yeah, it would, that would stop there. So therefore this must continue, which means this does connect because otherwise it would form 2 separate ends. Well, it touches itself also. So this has to be 5. It has to be 1, 2, 3, 4, and 6 here. So this is 1, 2, 3, 4, 6. This cannot be 7, 9, so this must be 5 and 8, which means this is 7, 9, this is 7, 9, because we have a 1, 2, 3, 4, 6 quintuplet in box 6. This can't be 5 or 8, which forces this to be 3, which means this can't be 3 or 8, so this must be 5, which makes that an 8. These can't be 6 here. This can't be 9, so this must be 7, which makes this a 9. These 2 cannot be part of the snake. Again, if you tried to break this up, this would have an end, and this would have an end, which is not allowed because we have 3 ends then, which would branch. So therefore, this connects here. This could actually go this way, so we don't know here. This doesn't have to continue that way. This is 3 digits adding up. This is in a 1 to 2 ratio, so this is 1, 2, 3, 4, 6, and 8. So 9 has to be one of these 2 cells. So therefore it must be consecutive with 8. So 8 cannot be any of these. This can't be 7, so where's a 7 in column 7? It has to be here. So this is 7, which makes this a 6. 6 is in a 1 to 2 ratio with 3, so this is 3, so this can't be 3. This can't be 3, this can't be 6, this can't be 6. This must be 1, 2, or 4. This is 7. This can't be 3 and 6 now, so 2 has to be one of these 2. We also have a 1, 2, 4 triplet in column 7, so that eliminates 1, 2, and 4 from the rest of the column, so therefore this must be 3. This can't be 2 because to form a 1 to 2 ratio, it has to have, it's either 1, 2 or 2, 4. This has to be a 5 because that's all that's left over in the column. Oh, and we had an 8 9 pair because 9 has to be consecutive with 8. And 9 cannot be here, 9 cannot be here, or here, so therefore 9 had to be here. Therefore, this can't be 3. This adds up to 10. So it's either 1, 9, 2, 8, 3, 7. It cannot be 4, 6 because the 4 is already in the column. This can't be 8 or 9, so this can't be 1 or 2. The remaining here are 1, 2, 4, and 6. Which works either way. The 9 has to be one of these 3, and it's likely in the snake. Because, well, it doesn't have to be. So, one of these 2 is a 2. So 2 has to be one of these 3. 5 has to be one of these 3. Actually, we've used up all the Kropke dots. So now it just has to add up to 16 for every segment. This has to be... So this adds up to 16 again. So if this is 9, this would be 7. So this could be 1, 6, or 3, 4. Or this is 8, in which case this adds up to 8. So it would be 1, 7, or it cannot be 3, 5 because of the 5. Eight and 9 can't be here. 8 and 9 can't be here. So this then has to be 8 or 9. Because if both 8 and 9 were in the snake, that would add up to 17, and that's already greater than what it can add up to. Therefore, one of 8 or 9 has to be here. Now we have an 8, 9, 8, 9 pair in row 7, which eliminates 8 and 9 from the rest of the row. So this can't be 8 or 9. This can't be 1 or 2. So now we have a 3, 7, 3, 7 pair in row 7, which eliminates 3 and 7 from the rest of the row. So this is 1, 2, or 6. This then has to be 1 or 6 again. So if this is... I think this has to be 1 then, right? If this is 8... this would have to be 1 and 7. It cannot be 2 and 6 because 2 is in one of these 3 cells. And, okay, well, 6 actually always has to be here. So 6 is always one of these 2 because there's no other place for 6 in the row. So if this is 9, this has to be 1 and 6 that way. If this is 8, this has to be 1 and 7 that way. Either way, it's a 1. So this can't be 1. This can't be 1. We have a 2, 4, 2, 4 pair in box 6, which eliminates 2 and 4 from the rest of the box, which makes this a 1. So these can't be 1. We have a 2, 4, 2, 4 pair there also. This can't be 1, so one of these must be a 1 because we know one of these is a 1. And this can't be... where's the 3 now in box 7? It has to be here. So this is a 3. This can't be 3. So 7... oh, where's 7? 7 can't be here. 7 can't be here. 7 can't be here. So this must be a 7, which means this must add up with 1 and 7, and therefore this must be 8, which makes this 9, which makes that 8. This can't be 1, so this is 2, which makes that 1, which makes that 2. These can't be 2. So it's 1, 4, 5. This can't be 1 or 2, so this is 6. 2 is one of these. This becomes, what, 2, 3, and 4? But this can't be 2 and 4, so this is 3. Neither of these can be 3. So this is now a 2, 4 pair also here. Interesting. The 9 then has to be one of these 2 cells. So the 9 cannot work with 7 with 3 digits to add up to 16 because there's another digit involved. So this must be 3, which makes this a 7. This then has to be 9 and 4 to add up to 16. So this must be a 5. We have a 4, 9, 4, 9 pair in row 8, which eliminates 4 from the rest of the row. So this must be 2, which makes this 4. The rest of these digits are 1, 2, and 6. Okay. What are the remaining digits here? 5, 8, 9, and 6. 5, 8, 9, 6. Can it be 6 and 9 here? No, because that would add up to 15, and we don't have a 1 here. This is specifically 1, 3 with 5 or 8. So it cannot be 6 and 9. It could be 5 and 9. So one of these has to be a 5 or an 8 here. So this cannot be 5 or 8. Therefore, this must be 6 or 9, right? We tried setting it to 6 or 9 just here. And that doesn't work because this then adds up to a minimum of 17. So we need a 5 or 8 in one of these cells. And we have 5 or 8 here, so therefore this can't be 5 or 8. So this must be 6 or 9. Can you ever have a 4 here? If this is 4... The problem is, if this is 4, how do you add up to 12? You can't, because there's no 3, 9, there's no 5, 7, and 4, 8's ruled out because of the 4. Therefore, this must be 2, this must be 4. These can't be 1. This can't be 1. This is 2, and it has to add up to 15. So it's 5, 9, or it's 6, 8, either way. Sorry, 14. And that works. So, Okay, so what happens? Well, can it ever go down? I don't think so, right? If it goes down, that means, well, not necessarily. It does have to continue this way. Interesting. So it could go here and then, well, yeah, this means that it can no longer snake back here because you would have a 2x2 region that's all snake. So it either goes down here and then goes to here. So this is one option. And then it would have to go here. But that, well, it would have to go down here, I think, right? Because then this would be a 2x2 area that is all non-snake if it doesn't go down here. Or I guess it could go something like this. Yeah, this is possible too. So it could go something like this to here, and then this is where it stops. Excuse me. Or it could go something like this. It can't go here. But it could go something like this, maybe. Connects to here to connect to here. But then this would connect this way. I don't think that's good, though, because, yeah, you have a 2x2 area, which is not allowed. So pink is not allowed. So we know either way, these all have to be snakes. This has to be a snake. Because we tried going down, and that didn't work. So we could go here. So it goes either here or here, and we're not sure which. This is 5 then. So this must be 6, which makes this must be 6, which makes this 7. This has to be 3. Which means this can't be 3, and this can't be 1 or this has to be 1 or 4. This has to be 5 because there's only 5 unique digits that add up to 16. And there's only one set of it, and it's basically Um, 1, 2, 3, 4, and 6. This can't be 6, so therefore this can't be 8. This can't be 3. This can't be 5. This is 8 or 9. This is 8 or 9. This is 3 digits adding up to 16, but we don't know. 2 of these digits must add up to 16. It could be 1, 6, but it could... So 4 can never be here. Right? If this is 4, it only adds up with 3 to add up to... how do you say it? To add up to 7, which is required to add up to 16 here. This can be 1, 2, 3, 4, and 6, but this can't be 3 or 6. This is also 1, 2, 3, 4, and 6. This can't be 3 or 2 or 6, so we have a 1, 4, 1, 4 pair in row 2, which eliminates 1 and 4 from the rest of the row. So this can't be 1. The remaining digits are 5, 7, 8, and 9, and this can't be 8. So we know we have a 7 in one of these two cells. This can't be 2. This can't be 4. There's no 3 in any of these cells. So we have a 7, therefore you cannot have a 9 in one, with the 7 in one of those cells. You could have an 8. That could be 8 and 1. And you could have a 5. Anyways, we have a 5, 7, 8 triplet now in row 2, which eliminates 5, 7, and 8 from the rest of the row. Therefore, this can't be 5 or 8, so this must be 9, which makes this a 5. This has to be 6. This can't be 6 anymore. This can't be 5, so this is 8, which makes that a 5. None of these can be 5, which makes that an 8. This can't be 8, and this can't be 8. This can't be 8, so this is a 5, 7 pair, which added together adds a 12, and we need 4 added to that. So this is 4, which makes this 1, which makes that 4, which makes this 1. So this can't be 4, this can't be 1, this can't be 1, and this can't be 1. So this adds up to 16. 4, 5, and 7. This can't be 4 anymore. We have a 1, 2, 4, 6. Well, actually, we have a 2, 4, 6. Triplet in box 5, which eliminates 1, 2, 4, and 6 from the rest of the box. Therefore, this cannot be 2. This must be 1, which means this can't be 1. Whereas the 1 in box 4, it has to be here. This has to be then 5 and 7. This can't be 1. This can't be 1, whereas the 1 in box 8, it has to be here. This can't be 4 anymore, so that makes that 9, which makes that 4. This can no longer be 4, so we have a 2, 6, 2, 6 pair here, which eliminates 2 and 6 from the rest of the box. So this is 4, this is 2, this is 4, this is 2, this is 4. This can't be 5 anymore. These can't be 8. Where is the 8 in box 2? It has to be here. So this is 8, this is 9, this is 8. This cannot be 1, 2. This cannot be 1 or 3, so the only remaining digit now is 2, which forces this to be 3. This is 6, this is 2, this is 6. This has to be 2, so then it has to go down. So it has to go down this way, and this is no longer a snake. And now we have the snake completely set. So this has to be a 5 to add up to 16. So this is 5, this is 7, this is 5, this can't be 2, this is 6, this has to be 7, the remaining digit now is 9, this can't be 1, this is 3, and this must be a 1. And that's the solution pretty interesting, actually. I'm not used to the snake set, but it's actually a very interesting. It's a higher restriction on the yin yang puzzle, so that makes it a little bit easier. Very cool. Very cool. I liked how the snake required certain things and therefore restricted certain numbers and restricted where it could go. Anyways, I hope you enjoyed the solve, and I'll see you next time on Frank Puzzles. Take care.